Welcome to part 6 of the OWON P4305 lab power supply review. In part 1 we covered basic operations, ripple on the outputs, on-off transients, mainly on transients, and then we skipped to the teardown because the display went dead. Card to that part here, link in the description. The next 4 parts were basically about my troubles with the display. You really don't have to watch them, but if you want to, go to the review playlists. There was already a card at the beginning in the video. I put links to all parts into the description. In this, hopefully last part of the review itself, I want to cover output stability, with changing loads and current constant and current voltage, accuracy of the display, and the details of the menu system and user interface. Enjoy! Let's start with output stability. The unit is currently set to 5 volts and my load is drawing 1.173 amps, and I will increase that to 2.35 amps and I will try to capture the step response on the oscilloscope. I hope I have my oscilloscope settings right now for single capture, so let's do that. Single capture, and I increase the load. We got something. We don't have to concern ourselves with that rebel here in the middle. That's just contact bouncing from my non-electronic load. What we're interested in is how much the voltage sagged before and after I changed the load. And if I mean that's a little bit subjective, but as I placed here the cursor line, we dropped 8 millivolts when we increased the current from about 1.15 amps to about 2.3 amps. And just to be complete, let's single capture the other way around. Let's have a look at that. Again, we see here double contact bouncing, but the important thing is, and I didn't move the cursor lines, the voltage is rising up again after we decrease the load from 2.3 amps to 1.15 amps again, by 8 millivolts. We're now operating in constant current mode with 1.5 amps, and I will halve the resistance of the load. So let's go into single capture and do it. Let's have a look. Okay, I'm at 10 millivolts per division. My shunt resistor I used for the current measurement is 1 ohm, so 1 ohm equals 1 amp, or 1 milliamp equals 1 millivolt, and maybe you can imagine that the current increased, but that's certainly less than 1 milliamp. But you really have to imagine it. Let's try it the other way around. I think I haven't shown that before, but of course my probe is now across that shunt resistor here. Okay, so let's try to single capture the other way around with increasing resistance. There we have it. This time there's actually a little drop here, and 3 millivolts, so 3 milliamps. Let me try to measure that here at the bottom of the noise. And again, this is subjective where you place your cursor lines, but this time I got 2 millivolts or 2 milliamps, so let's go with 2.5 milliamps. And that's what I measured at constant voltage, 5 volts, increasing the load from 1.15 amps to 2.3 amps. I got a delta of minus 8 millivolts, so minus 0.16%. And yeah, exactly the reverse if I decrease the load. In constant current mode, delivering 1.5 amps, and I calculated from the output voltage the resistance of the load. So decreasing the load resistance from 6.3 ohms to 2.3 ohms, I measured a delta of less than 1 milliamp or less than 0.067%. And the other way around, yeah, increasing the load resistance, I measured a delta of minus 2.5 milliamps or minus 0.67%. Correction, minus 0.167%. If we have a look into the spec sheet, we see that on load regulation for constant voltage mode, it says less than 0.04% plus 3 millivolts for 0 to 100% load. That's a lot less, even if we take, subtract the 3 millivolts from our 8 millivolts measured, we still have 5 millivolts, and that's still 0.1%, and we varied the load just from 1.15 amps to 2.3 amps, so not from 0 to 100%. What we measured for the load regulation in constant current mode is much more along the line of the specification. Again here the plus 3 milliamps, and all our deltas we measured were 1 milliamps and 2.5 milliamps, so less than 3 milliamps. So that would be within the specification. However, we didn't vary the load between 90% and 10% of the rated voltage, just between 9.5 volts and 3.4 volts. But an oscilloscope is not a precision measurement instrument, at least not for voltages. So let's try to verify our result with my Bryman multimeter. Yeah, and you notice the voltage is a little bit lower. That's because our shunt resistor is no longer in the circuit. So we are still in constant current mode, 1.5 amps, and I halve the load resistance. And yeah, I can't really say that there's at least a milliamp change. So let's go the other route and increase the load resistance again. Nope, nothing. So whatever we measured with that oscilloscope, it's within measurement errors. Let's try constant voltage too. We're back in constant voltage mode, 5 volts, 1.18 amps this time, and I tried to connect the leads of my multimeter as close back to the unit here on the post as possible to avoid any voltage drops due to the current flowing. And I will, we're reading here 4.996 volts. And I will double now the load. And we're losing 5 millivolts. And but the internal display, please note that, and I guess the voltage feedback loop is based on that, it doesn't twitch at all. So I halve the load again, and we're 5 millivolts up. And here it didn't twitch. So that leads me to the conclusion that all we measured, the few millivolts drop while increasing or decreasing the load from 1.15 to 2.3 amps, that's all voltage drop here in the posts and in the cables and the circuit board leading up to the posts after the unit takes its measurements or takes its voltage feedback. That's the reason there are more expensive lab power supplies out there which provide you 2 additional posts where you can have an external voltage feedback. But yeah, bottom line, voltage regulation of that thing, besides what we measured, and current regulation too, is well within specs and very good. Lastly, I want to see how precise the voltage and current display here is. So 9.999, 10 volts and 10 volts on my Bryman. At 1 volt set voltage I got 0.999 and yeah, let's say 1.000. At 100 millivolts 0.099 and 99.4 millivolts. And at 10 millivolts 0.010 and 9.37. Let's say 37. Constant current 10 milliamps. I read here 0.010 and here, yeah, let's say 10 milliamps. At 100 milliamps 0.100 amps and 99.9 milliamps. And at 1 amp I read 1.000 and yeah, let's say 1.000. I don't think we need to break out the calculator here. Yeah, the differences between the Bryman and the OWON display, and yeah, I think I switched here the columns a little bit around. It's, yeah, at most 1 digit. And if we have a look into the spec sheet, yeah, readback, resolution, value, voltage and current, forget about the percent values, is plus 10 millivolts, so 10 digits, yeah, according to spec. And for the current, 5 milliamps, so 5 digits. Yeah, we never exceeded that. That just leaves us with, yeah, the system and other menus. So in the system menu, you find, yeah, the backlight. Default is 50 and you can increase that, but that does nothing for you. Yeah, side note, you can stay on the button and there is no, yeah, button repeat or something. You can turn the brightness of the display down. So that is working, but yeah, I usually leave it at the brightest setting. Next we have language. You can choose between English and simplify Chinese. You can turn the beeper on and off. I leave it off now. And you can decide in which display mode the unit should come on. Currently, yeah, we saw that all the time, it's number, but you can also have a curve, so a graph, either current or volt, and the time scale can be, so yeah, whole axis 30 seconds or 60 seconds. I leave it at volt, number. That's for the main utility menu. You can configure the port, the RS232 port at the back. It says only port here. I will come to that back in a second. Anyway, that's 115,200 is the maximum baud rate, and you can go down to 2,400. You can decide if you want odd, even, odd parity bit or non-parity bit. Yeah, even is also possible. Okay, non-parity, please. And the number of stop bits, 1 or 2. That's it. And then you have the system submenu in the system menu, which gives you just the model number, the version, the serial number, and the checksum of the flash memory. you can set everything back to defaults and you can do a key test. Wow. Great, huh? Yeah, that's it. And you leave that, but it's always here. Help is always here at the bottom. That's very neat. You can leave it here. The memory menu just gives you 5 memory slots, and yeah, that's probably a little bit small, but that's 24 volts, 3 amps, and yeah, just by OK, I can recall these settings. Interesting thing about this, and you have 5 positions, there's obviously no way to save your current settings to memory. Instead, you have to go here to edit, and there you can edit the positions for the memory slots M1 to M5. A little bit curious, but yeah, that's what it is. And finally, you have a keylog function, which can come in handy. So you just press keylog. For prolonged time, and yeah, the unit is locked. And to unlock it, you press keylog again for prolonged time. We already saw in the system menu that there's something like a graph function, and this is also directly accessible here via the yellow OK button. If you press that, you end up in the current graph for 30 seconds, and you can change that via up and down to the voltage graph and back, always 30 seconds. If you want the 60 seconds display time frame here, you have to go through the system menu. Otherwise, you can access your set voltage and current via the left and right cursor keys and change them accordingly. Yeah, and yeah, press on that button also brings you back to the normal numeric display. I had planned a segment showing you how to remote control the unit via its RS232 interface here at the back using OWON's remote control software. Turns out there's no such thing. What you can do, you can send text commands via that RS232 interface to the unit and control it that way. And you can also query what it's currently doing, yeah, voltage output, etc., the readings. However, I'm a little bit ambivalent about calling this an RS232 port because it isn't. It doesn't fully comply to RS232 standards in regard to the voltage levels. You can see that on the oscilloscope, of course, in this video card here, link in the description, where I tested a Chinese USB to RS232 converter, and there I stumbled upon the fact that, yeah, the voltage level are not RS232 conformant. The RS232 chip inside is a ZPEX SP202EEN. That SP202E is a perfectly good RS232 transceiver. You have a 5 volt side here and you have a, I guess, plus minus 10 volt side here. And the plus minus 10 volts are generated via 2 charge pumps, a voltage doubler from 5 volt to 10 volt, and then a voltage inverter from plus 10 volt to minus 10 volts. And they need 4 small 0.1 microfarad capacitors. And because charge pumps, capacitor-based charge pumps are real strain on your power rail, you also need a huge 10 microfarad decoupling capacitor here. But what can go wrong? I mean, in the aforementioned video, I measured almost minus 1 volt and maybe a little over 5 volt. Why? On the RS232 interface board, we only find 1, 2, 3, 4 capacitors, and they seem to be all of the same size, so I guess these are the small 0.1 microfarad capacitors for the charge pumps, and the larger 1 microfarad capacitor for decoupling is missing. If you take into consideration that the power supply for the RS232 daughter board, ground and 5 volts, I guess, is going through 2 thin copper strips in this very long flat flex cable to the front panel, then it's no wonder that the charge pumps do not perform as expected. Time for the wrap up. The good, the bad, and the ugly. Let's start with the good. For less than $200, you get a 150 watt linear bench power supply in a compact package with a, adequate build quality, low output ripple, good load regulation, and at least in my opinion, a nice user interface. I'm ignoring here that my unit had trouble with the display. That might have just been, a production fluke or whatever. So, what's bad about it? The most obvious is the noise. You don't have to push it to 100 watts or 150 watts to set the engine in the back to toga thrust. I remember, 30 watts are enough to, spin the fan in the back up to a, really annoying noise level. Then there's the RS232 interface, which is almost RS232 compliant, but they cheaped out on a 10 microfarad decoupling capacitor, and those, devalued that functionality enormously. So you can connect this thing to any industrial RS232 device, delivering plus minus 15 volts on the data lines, and it will survive and it will understand that device. The other way around, if each and every RS232 device will understand the OWON, so data in the other direction, that's questionable. The ugly thing about that unit are the on transients. The off transients are okay, but the on transients in constant voltage mode range from perfect, absolutely no overshoot with low loads, to, at high voltages and high loads, acceptable with 5% overshoots, but then at high loads at lower voltages, you get 10% overshoots. And that's not really acceptable if you, working with sensitive 3.3 volt circuitry. And the overshoots in constant current mode are simply atrocious. I had watched part 1, but I have, out of my head, 50% overshoot. No problem. All that leaves me with 2 questions. First, is the equivalent unit from Corad that goes for $100 or even less so much worse than the OWON? And second, is the equivalent unit from Rigel that goes, I think, for $350 or $400 so much better? Anyway, that's it for today. Till next time, bye!